So, as we get into separations, it is probably where you are going to see at least 50% of analytical chemistry jobs. Probably 90% are going to involve separations in some way, either as a preparatory step or part of a combined technique or some way along the way. And so really, in some ways, this is going to be the most relevant chapter to people who are looking to get a job in chemistry, because your two main fields of chemistry when it comes to getting a job are going to be organic synthesis of some sort, or they're going to be analysis. And if you're in analysis, at least half of those jobs are going to involve separations in some way. So that's why this is an important chapter. We're just going to be able to hit up some of the fundamentals and give you kind of a flavor for what they are. We did do 2 separations in lab where we did an HPLC and we did GCMS analysis. The HPLC is a little bit more education grade, a little bit simpler, but that GC that we did in lab, that is like industry standard. You guys will all get jobs. You're all smarter than me. Come on. And if it's, I mean, it depends on what you're going for. Like, do you count my job as an actual job? Some people don't. So yeah, no, you guys are going to get jobs. All right, so let's go into analytical separations. All right, so this is our introduction to analytical separations. All right, so if you remember, analysis comes from the Greek. It comes from the words lysis or splitting, and it's the opposite of synthesis, which is combining things together. And thus, separation science, or the art of unmixing, is analysis in the truest sense of the word, and that a sample comprised of a mixture is broken down into smaller volumes of less complex mixtures or pure substances. Right? So making mixtures is easy, right? Nature wants things to be evenly distributed, right? So if I take a red Kool-Aid and a blue Kool-Aid and I mix them together, I end up with purple, right? What you don't see is unmixing happening, where I pour the purple out and it goes into blue, and I pour it out and it goes into red. Unmixing things is hard because you have to fight that entropic distribution, that property in nature where you want to get the largest possible number of microstates. So you want to physically distribute the red and the blue as evenly as possible. And you've got to fight that entropy in order to get your pure substances back out. And that's really common. You think about something like pulling ore out of the ground, and you want to get iron out of your iron ore. You've got to put energy into that, because rather than having your distributed system or something that's already reacted with oxygen to form an iron oxide, you've got to put energy in that system to get back to the pure substance that you want. So this unmixing step is hard, but obviously it's not impossible to do. Right? And if we were live, I would do a cool little demo where you can get some bromocresol green, and then like you set it up so that you've got a bromocresol green mixture in a container, and then into 2 target containers, you got a little drop of acid at the bottom and a little drop of base at the bottom, so that when you pour it in, the one becomes blue and then the other becomes yellow, and you're like, look, I magically unmixed them. So, pro magic tip there, kids. So how do we go about getting pure samples or substances? So there has to be a way for us to fight against Mother Nature. Well, maybe not Cocaine Bear, which I just read about. Don't fight Cocaine Bear. The difference is, and we're going to do that by taking we're looking at the differences in physical or chemical properties of matter to separate one substance from another substance. Right, so this is definitely a physical process, right? Our separation is moving groups of molecules of one type, and pulling them apart from groups of molecules of a different type. And we got a bunch of different separations techniques that are out there. So separations is a broad kind of umbrella term for, unmixing things, right? So a real simple, probably the oldest separation out there is going to be distillation. right? So distillation, you're looking at differences in the vapor pressure between a two-component mixture, right? So you can't do distillation on really complex mixtures. It's never going to give you a 100% pure distillation. That's why if you're running a still, you let the first gallon or so come off, and then you throw that away because it's going to have a lot of methanol in it. And then you take like the later cuts that are going to have more ethanol in it. If you fight Cocaine Bear, just please record it so we can see. That's all I ask. Distillation, really, obviously, really important. Big money in distillation. Extraction is another very common separation that you have probably done in organic chemistry. I do not know because I've not taken organic chemistry here. But this guy right here, this little separatory funnel for doing separations. Have you guys seen those? Just somebody give me a thumbs up, yay or nay, if this is a piece of glassware that you have come across. Yes, okay, whew, thank goodness, right? So it's really common, right? So you take something and you've got some molecules and you've got an aqueous phase and an organic phase, and you shake the thing up, and then it's either whatever you're synthesizing is either going to go to the organic phase or the aqueous phase. And dude, that always confused the heck out of me, and I could never remember which one was which. And then somebody was like, oil floats on water, dumbass. I'm like, oh, that makes it so simple. Okay, so you got your aqueous phase, you got your organic phase. You are doing a separation there based on your hydrophobicity or your polarity. So that's another physical difference. Supercritical fluid extraction, that is another type of extraction. Some people might throw that in with chromatography, but that's how they make decaffeinated coffee, is with the supercritical carbon dioxide extraction of the caffeine. I suppose it's good in the sense that some people want decaffeinated coffee, they can have it, and you get leftover caffeine, and you can make recaffeinated coffee for the rest of us who love caffeine. But we're going to focus on chromatography. Right? We're going to look at gas and liquid chromatography. There are other kinds of chromatography in there, something like capillary electrophoresis we'll look at, or we won't really cover thin layer chromatography. So this paper chromatography would be like a thin layer chromatography. But we're going to look at chromatography using gases or liquids, and we're going to put them through tubes. The differences between chromatography and extraction or distillation is that these guys tend to be pretty bulk separations, right? I want to do a lot of stuff. I want to make, gallons and gallons of Jim Beam, or I want to get a lot of crystals, so I can mass them out and figure out what my product is and get a melting point. That was seriously like all organic chemistry lab was for me. Take stuff up in a separatory funnel, do the vacuum filtration, you got a white crystal, you take a melting point. And then like one time, it's like, ooh, you get a yellow crystal. Right, so in organic chemistry, for those of you who have taken it, for those of you who have not taken it yet, we get to make all sorts of pretty colorful compounds in inorganic chemistry. That's where the colors are at. Chromatography is an analytical technique. So we're going to look at chromatography as an analytical separation where we're trying to identify and quantitate things rather than just go for, I got a bunch of stuff, no, I want to get some of it purified, or I want to do a large scale separation. So this step here is why taking street drugs is a no-no, kids, because how good is whoever you're buying from at making and purifying your compounds, right? Think about what your percent yields are in organic chemistry, and like, okay, well, if it's an 80% yield, what's the rest of the stuff? The chromatography comes from Greek words, chromos, or chroma, meaning color, and graphein, meaning to write. So this is color writing. So chromatography is a way for us to separate two or more chemical compounds, for example, proteins. And there are different kinds of chromatography. In general, chromatography takes advantage of the differences in the chemicals you want to separate. So it could be size, it could be electrical charge, it could be charge to mass ratio, the ability to bind materials such as affinity, it could be polarity. There's lots of different ways. So here's the developments of chromatography, just kind of on a timeline. So it's a, you know, relatively new, uh, relatively-ish new branch of science. So Suet, this guy Suet, he was kind of the first one to outline the principles, and so he was doing uh, plant pigments, and he was using a column where he was taking chalk, so basically taking plant pigments, and here's this big tube, and he put some chalk powder in it and put some solvent on the top, and it's like, oh, look at that, and we're going to separate out some chlorophyll, beta carotene. Lederer and Kuhn were the first to do some LC applications. They were looking at carotenoids. Again, this is still with colorful compounds. First book on chromatography came out in the mid 30s, right? So you're starting to gear up for World War II around here. TLC is thin layer chromatography and ion exchange. We're not going to cover too much about ion exchange, but when you start getting a little bit more sophisticated synthesis techniques coming in, so in the late 30s, you've got these synthetic ion exchange resins, which are able to do another type of chromatography. It's not until the 1950s that you actually have reverse phase liquid chromatography being described. So probably 80%, most of the separations we're going to see and most of the columns we're going to see are going to be what's called a reverse phase LC column. And instrumental HPLC doesn't really start until the 1960s, the mid 1960s. And HPLC, that's the high performance liquid chromatography, when you can start to get some of the mechanical and instrumentational problems solved that will greatly improve both your throughput and your ability to separate compounds. So some of the properties that we can use, we're relying on physical differences or chemical differences between molecules. So something like size can be a factor. So size exclusion chromatography. It could be charge in an ion exchange. It could be electrophoretic mobility, so an electrophoretic gel or capillary electrophoresis. So electrophoretic gels, everybody has seen one of these. So somebody like, if you're on a TV show and somebody's like, oh, go run the genetic analysis and show me the DNA scan, they're probably going to show you a picture of an electrophoretic gel. Those are the ones with all those bands in a column. Capillary electrophoresis is a by far more efficient technique, and I've got a good story about that when we get to it. Hydrophobicity or polarity, so our normal reverse phase, GC or LC columns, that's what we used in our HPLC lab, was we took advantage of a difference in hydrophobicity or polarity. It could be chemical or biological effect. So most separations are going to be conducted either on a gel or on a column. So the principle is roughly the same. You guys have probably all seen at some point in your sciencing careers or just out in nature this phenomenon where I've got a piece of paper and I put some spots of ink on it, and it's got a liquid down at the bottom, and as the liquid travels up, it's going to carry some of those pigments with it, but it's not going to carry all of those pigments equally. You're going to affect a separation of some of those components. Okay? We are going to not do things on a column in an analytical approach. We're not going to do it on a paper in an analytical approach. We're going to do it on a column instead. So instead of having a piece of paper, we've got some sort of solid matrix. We put a sample on the top, and then you're going to start to slowly dump solvent or something from a reservoir. And as the solvent pushes the material through the column, you end up separating your components. So you're still traveling, but here it's traveling downwards instead of upwards. As you had your component mixture, the green will be differentially attracted to the stationary phase, whatever this solid matrix is, relative to the red component. And so the red component will come out first, and the word for that is elute, so it will elute first. And then you'll have a gap, and then the green component will come out second, right? So there's a gap in between here, which we will see as a part where we're just getting solvent through, or something we can't see. And then we'll start to see the green coming through at the other end. Now, there are bulk separation methods that you can use, and people often do. Like if you're in a synthesis lab, you may have a column that looks almost exactly like this, and it might be a big, honking big tube. That might be like a full 2 liters in size. And you put your compound on the top and you start pouring solvent down it, and you will deliberately collect individual, what are called fractions of the eluate. So part of the stuff that comes off, you'll grab that and you'll pick it up and you're like, oh, look, I got a thing full of red stuff. How do I got a thing full of green stuff? And usually you're not looking for something red or green. There may be other things in here that you just cannot see. If something's absorbing in the UV, there might be another band in here that we just cannot see. If you look up here at this part, right, we have started to unmix these things, but we have not fully separated them. Right, so this is where these two bands are together, right? We want to get them separated. And we will talk a lot about like, well, how do you get that separation to be efficient, and how do you really get those two things separate from each other? Right? So this is a very, very primitive example of the same thing. We got a mixture of A and B. As we start to pour mobile phase down it, we're going to separate out bands A and B. This is a little bit better picture because you can see that as A and B get further and further down that column, rather than starting off as this very narrow strip, right? B gets broader, right? It gets broader out over time, and the same thing happens with A. Right? That mobile phase, right, could be lots of different things. It could be polar, it could be non-polar. One of the more popular stationary phases, or the fillings that you can pack the column with, is graphitized carbon black. It is a very popular packing material. It's got something like 2,000 square feet per gram. And if you take PChem with me, we will actually do a calculation on how many square feet per gram is a graphitic carbon. You could use alumina particles. You can use diatomaceous earth, right? Chalk or zeolites. And diatomaceous earth is kind of cool. So these are pictures of some diatoms. So if you put chalk out to like kill slugs, now imagine you're a slug and you're running over one of these things, right? Slugs do not have a lot of armor on the bottom. So that slug foot is pretty prone to getting punctured by these like little caltrop throwing star Lego shapes. So bad if you're a slug, cool looking if you're a scientist. That's diatomaceous earth. Zeolites are just mineral structures that have a high surface area. That's the stuff with a high surface area. Graphitized carbon black, that is the stuff in your water filters. So if you buy yourself a Brita water filter, it is really just a packed column, and your mobile phase is water, and all the other crap that you don't want to drink is going to get retained on this stationary phase. So that's why it is very important that you change those filters out, because eventually, after months and months and months, so let's say we've got some benzene here, right? The benzene is going to stick on that top. It's going to come out very, very slowly. But you do not want to be at the point where your benzene is starting to elute from your column. You want to throw your Brita filter out when it's still somewhere up in here, right? And so the benzene and all the yucky stuff is still trapped in that graphitized carbon black, and you haven't flushed it all out down to the bottom, because at some point you're going to get like a big old slug of whatever contaminant it is that you're trying not to drink. That's just, so if the zombie apocalypse happens, right, make sure to change your graphitized carbon black filters on the regular. If we look at the output, right, so down here at the very bottom where we've got this detector, right, the time 0, 1, 2, 3, and 4, now we can make a recording and look at a detector signal at time 0, 1, 2, 3. Oh, I got some stuff coming out. 3.5, nothing. 4B starts to come out. So we can make a trace over time of what's happening to a detector's response at the end of the column as things start to elute and come off the end of that column. All right, so if we take that, we can kind of like project that sideways, and we're going to see okay, here's B coming off, and here's A coming off, and then here's B. Okay. Absorption chromatography shows that big molecules go through the column more slowly, right? So if you think about just this size-based separation, I've got this packed column, I've got something big molecule, and it's got to make its way through this packed surface, right? This packed volume. The bigger you are, the more slowly it's going to go through. Right? The longer the path length you've got, the greater the difference between the elution times. So if I made a really, really long column, those differences between A and B, even if they're small, because it's got such a long way to go, is going to show up, right? So if you think about two people who are running a race, even if somebody is running a 9-minute mile and somebody's running an 8-minute 50 mile, the longer that race is, the greater the difference between when person 1 gets to the finish line and when person 2 gets to the finish line. So you get that column nice and long, and it's going to increase the differences between the absolute difference between A and B, even though the relative difference in performance, the rate is going to be constant. If you got a bigger molecule, right? You got more surface area. So that's another way to separate things. If you put more surface area on there, you can get a tighter packing column. So if you get a teeny tiny particle for your packing material, then you're going to have more surface area. You could increase the porosity of your particles. So I've got a particle that's a solid ball that's making up my stuffing inside my column. But if I make it a hollow ball, like a wiffle ball, well, then I've increased the surface area. Right? It's like getting through a crowded room at a party to get to the beer keg in the kitchen. Right? If I've got a room that is packed full of people, right, it's going to be harder to get there. Right? So if I take a room and I pack it full of, people and it's a very busy party, it's going to take me a while to get to that beer keg in the kitchen. If I am a big bulky person, right, I'm going to have a harder time getting through that room than like a little kid would. Not that they should be they're going to get some root beer. Right? Our neighbors used to have really awesome tailgate parties, and eventually, when they started to have kids, they switched out the traditional beer keg with a root beer keg. And let me just say, as a 10-year-old, and you get to go up and you get to tap that root beer keg, it is a pretty bomb ass feeling. So if you got the money, do your kids a favor and get them a root beer keg at some point. So it's like getting through a tight confined space that is highly packed. You've got a lot of things to traverse. It's difficult. Okay? You could also do your separation based on a partitioning concept. So imagine your separatory funnel again. So in your separatory funnel, you've got something that is hanging out. It could be either in the aqueous phase, right? But it's a little bit more organic. It's going to spend some time in both the aqueous phase and in the organic phase, right? So if I've got my molecule, right, and let's say it's a non-polar molecule, it's going to spend most of its time up in the organic phase, and it's going to spend a little bit of its time down in the aqueous phase, right? So it's never going to be completely efficient, where I'm going to end up with all of my analyte molecules up in the organic phase and none of them down in the aqueous phase. But I am going to have some sort of ratio to the time they spend in the organic phase and the time they spend in the aqueous phase, and that's going to be the same as the concentration in the organic phase and the concentration in the aqueous phase. And if I've got a products over reactants type of thing, I can come up with a K expression for that, right? So this K expression is just how much of my analyte do I have in my polar phase divided by how much do I have in my aqueous phase. So my product, or my synthetic product, is going to end up in the organic phase. How much ends up in the organic phase? How much stays down in the aqueous phase? So, if you did not end up with 100% yield doing some of your organic syntheses, this is partially why, right? Sometimes they're going to spend some time down in the aqueous phase. And so when you open this guy up and you drain out your aqueous phase, right, you're going to drain away some of your molecules. But this partition coefficient is going to be how much do you have in one phase divided by how much you've got in the other phase. We can take that same concept and stick it onto a silica surface using silane chemistry. Right? So we're going to have a column wall that's made out of glass or a bead, right? A silica bead, and we're going to coat that bead with a layer of silica reactive molecules, the silane molecules that are going to have this greasy chain on it, this greasy hydrocarbon chain, and we're going to partition between the mobile phase, which would be aqueous, and our stationary phase, which would be hydrophobic or non-polar, right? So we've got some sort of hexane chain. Our molecule here is going to spend some time in the mobile phase and some time in the stationary phase, and I can come up with a ratio of, just like on here, how much was in the polar and how much was in the aqueous phase. Right? So I could either do that as concentration or how long, right? So that partition coefficient, we could look at that in terms of like time, or we can look at that in terms of concentration. But right now, just think about it as concentration, right? So it's going to concentration go up in here and concentration down in here. The reason why we can think about it in time is that this mobile phase is mobile. When we did the shaky thing, right, we weren't really worried about this thing moving around, right? We weren't refreshing the organic phase or pulling out our aqueous phase. Here, this mobile phase is moving along. And so that partition coefficient becomes important because when you're in the mobile phase, right, your molecule gets moved along. When you're in the stationary phase, it stays put. And so the amount of time it spends in that mobile phase, so the concentration in the mobile phase, is going to determine how soon it exits the column. If you've got something that spends a lot of time in the aqueous phase, it's going to spend a lot of time in that mobile phase, right? The concentration in here is high, it's going to come out soon, rather than something that's going to spend a lot of time in the stationary phase. It'll come out slower. Right? We have two types of column geometry that we can use. So you can take that organic phase and stick it onto the silica surface using silane chemistry, and we can coat the walls of a tube. So this is like a capillary or a smooth bore column. This is like what we're going to use for our GC. Or we can take a bead, like a silica bead, and then we can coat that bead with our silane. And that's what we use for a packed column. So this is like what we've used for HPLC. Can you have columns of different kinds with HPLC versus GC? Yes, yeah, you can. But generally speaking, these kind of open tube or smooth bore columns are going to be way more prevalent in GC. And these kind of packed columns are going to be way more prevalent in LC. Okay? And you've got different combinations or a matrix of things based on what the column is made out of, whether it's normal phase or reverse phase. So reverse phase, I drew this as kind of bigger because most of our separations that we're going to see are going to be on reverse phase columns where the stationary phase is non-polar. All right, so let me add that with the pen. So this is a non-polar this guy's going to be polar. So we have a lot more reverse phase than normal phase columns out there. You can further divide it as to whether something is going to be a packed column or a smooth column. So you've got what's the column made out of and what's the geometry of the column. And it's about 50-50 whether they're packed or smooth. These guys generally tend to be, like I said, in the GC, and these packed columns generally tend to be more prevalent in LC. Not to be confused with LSA. So our partition chromatography, we got a liquid-liquid chromatography. That's a physical absorption process. We can have a liquid bonded phase. That's a chemical bonding that happens. We can have a normal phase where you've got a polar stationary phase and a non-polar mobile phase, where your least polar solvent elutes first, or least polar analyte elutes first. You can have a reverse phase where the most polar thing elutes first. You're going to have your best separation when the polarity of the analyte and the stationary phase match. So if you were looking for something that is a polar compound, you're going to want to run a normal phase column. If you're looking at something that is going to be, more organic and a little bit less polar, then you're going to want to run a reverse phase column. There are fancy columns you can get now that are that do all kinds of different things, like separate things that have a chiral component to them. So doing a chiral separation is really difficult. I need to add a little bit more at the end of this slide deck about that, because chiral separations are hugely important, because when you are looking at different drug compounds, chirality matters a lot, right? So I've got a kid who's got asthma, and one of the things he takes is albuterol. Albuterol is a molecule that comes in two different forms. It's got a left-handed form and a right-handed chiral form, and everybody knows what chirality is, right? If you don't, just ask me. But different molecules can have different handedness, and the L-buterol is the active compound, and the R-buterol, the right-handed form, is the dextrobuterol, sorry, the D-buterol, is the inactive compound for most people. And so it is really difficult to do that chiral separation and purify just the left-handed molecule. But for some kids, or some people, including my kid, if you get that dextrobuterol in there, it acts and just absolutely keys a person up, and it can act to accelerate heart rate, and you've got other side effects. And so we have to buy the L-buterol, which is the purified form, and it's more expensive. Same thing with if you're taking ecstasy. Ecstasy is a chiral compound. One is happy fun times, the other is like melt your brain bad times. Again, don't buy a street drug. Don't buy a street drug, kids, because like how good is whoever you're buying it from at doing chiral separations too? That's a big issue for pharmaceutical companies that are doing that chiral separations. All right, one other cool chiral separation story is doing chiral synthesis is actually pretty tricky too. So when you make these molecules, nature is really good and very dependent on you having molecules of the right-handedness. So if you've ever played Mass Effect, which is a fantastic game, there's a couple of alien species in there that rely on differently handed proteins, and it's a very minor plot point, but it's really fascinating in that you can't have the same food supply for both of them, for both humans and these aliens. The same thing happens with our DNA, so our DNA has one chirality to it. Our proteins and our amino acids, they tend to want to be in a particular chirality. And so there's a lot of stuff and checks that nature has that kind of pushes things in one direction. When we make a synthetic product, we have a lot harder time specifying, I want to make just the left-handed molecule, or I want to make just the right-handed molecule during a synthesis. No, you wish. Making ecstasy is a little bit more complicated. What's really easy to make? Heroin. Heroin's super easy to make. Not that I suggest making heroin either, but that's really just you're taking morphine, you're taking opium, and you're doing a real simple extraction to get morphine, and then you throw in some acetic acid. You basically mix it with vinegar, and you put two carboxylic acid groups instead of one carboxylic acid group on there, and so you basically double the effectiveness of it. Anyway, I was getting back. This actually is about drugs. So the synthesizing stuff with chirality to it is tricky. Right? So we're going to talk about separating things with chirality, but even synthesizing things with chirality is difficult. Nature is really good at it. And so you can actually kind of push synthesis to make a chiral molecule if you throw in what's called a resolving compound. So something that already has a chirality to it. And then when you do that synthesis, it kind of like pushes that balance over to let me make more of one form versus the other. And a really good traditional soluble, good performance characteristics compound that you could throw in as a resolving compound was cocaine. And so a lot of labs in the 30s, 40s, 50s had a decent supply of cocaine on hand so that they could do these syntheses. And in college, when I was in college and they were like cleaning out some of the stock rooms, it was like, okay, fire drill everybody, because they had found somebody's old lab and they had like a kilogram worth of cocaine. And like, you know, the ATF people showed up and they're like, you know, woo, they came in and they're like, yeah, here we go. We have like this kilograms worth of cocaine. Could you please do something with it? I'm sure all the guys back in the truck were like, yeah, 2 kilos of cocaine, awesome. So it's making chiral compounds is tricky. So anyway, back to some of our key concepts for separating things. Right? So we said we got this partition coefficient, and we're going to call it big K, not to be confused with big K Mart. Totally different, but big K. Remember, that's going to be our concentration in the polar versus our non-polar versus our aqueous phase. Now looks like an AG, AQ, right? And that's our K. Right? So what's our concentration in our organic phase? What's the concentration in our aqueous phase? Right? We have another term, and that's retention time. So that's how long does it take for an analyte to elute. So related to that is our velocity. Right? And our velocity, the speed at which it transits the column, is going to be related to how long it takes versus how long the column is. Right? So that's just like any time distance type of equation. We've got this other thing here, this term H, and this is going to be the height of a theoretical plate. Right? And you can think of this as the thickness of the polar-nonpolar interface. That's not where the term plate comes from. It actually comes from a old distillation type of apparatus, and I can come up with a picture for it, but it's a dumb term. So you've got this thing. So if you think about that polar-nonpolar interface, like when you have that separatory funnel, there was that like little interfacey region, right? The thicker that is, right, that's going to be related to how thick your plate height is. You want that to be as small as possible, right? That way you can get more plates, more theoretical plates inside your separation and inside your column. So you can kind of think of your separatory column as being like a series of very, very small separatory funnels. The thinner the plate, the thinner that interface, the more of those teeny little columns you can get. Right? And then resolution, R sub S, is going to be when two species are sufficiently separated. And you're like, well, what does that mean? What do you mean sufficiently separated? Well, you kind of know what separated means. If you're looking at a chromatogram, you get a little peak, and you don't want the two peaks bumping into each other. If you've got yellow and blue, you don't want any green in the middle. You don't want any overlap. Right? So it's when you get the two things adequately distance from each other. Right, so if you've got a really, really long column, right, it gives more time for those solvent or those analyte molecules to interact with the stationary phase. And so the retention times are going to change. So if we got a nice long column, right, our relative small differences between A and B's affinity for the stationary phase will become more pronounced. Right? So if you go further, right, they're going to come out at a longer time. but notice that these guys are going to be broader. Right? And we'll talk about why they're going to be broader. If you push everything through fast, you get sharp peaks. The longer your column gets, the broader those peaks get, and the longer it takes for you to get through the column. And so there's a trade-off that you've got to make. So as your things go from like, you know, narrow to broader, you know, what game is going to give you the most optimal separation? Because I'm fighting two different things, right? The longer I put it on my column, the further apart A and B are going to be, but then the broader these are going to be. And so at some point, you know, even though I've moved their peak positions further apart, maybe these tails start to run into each other. Right? So our peaks are going to broaden out. They're going to get less high. They're going to distribute that. The area under that curve is going to correspond to the amount of analyte that you've got. Right? So how do you increase those separations? Right? There's two different ways. So if I've got some sort of, you know, yellow and blue component, right, and I got overlap and I got some green in the middle, I've got two ways to do it. One is to move these peaks apart from each other and keep them the same shape. And the other is to narrow those peaks up so that in between I've got less of a gap, or I've got more of a gap, right? I don't have as much bleed through. So if you want to think about this in terms of our statistics, right? Here we've got some sort of mu, and over here we've got some sort of standard deviation or spread in our data. These are, in theory, very Gaussian peaks. And so we can use those terms like mu or our retention time, right? We can change our retention time. And we can also look at the peak widths as well, right? Because that's going to be talking about the spread of our molecules. In this case, we're talking about a physical spread, right? Or a temporal spread over time in our molecules, as opposed to a spread in our data. Our migration rates, right? We can look at a chromatogram. We've got a couple of different parameters. We've got retention time. That's between time 0, right, when you do your injection. That's going to be T equals 0. So the time between when you first do your injection and where the peak shows up, that's a retention time. So that's the retention time for peak number 2, right? You're also going to have a retention time for peak number 1. Right? This would be T sub R1. For that first peak, though, we're going to give it a special name, and that's T sub M. So that's going to be how long is it going to take for nothing to get through this column. So whatever our non-retained stuff is, we're going to call that T sub M. These are the things that are coming off the column with no interaction in that stationary phase. Right? So this is just the amount of stuff that, or the amount of time it's going to take from our initial mobile phase to get through and our non-retained stuff. Right? We then have this T sub S, which is the difference between our TM and our retention time, right? And this is our non-retained peak. It takes no time for the molecules to get through it. It's also called the dead time. So let's skull here. Okay? It's our dead time. So this is TM from the mobile phase. Our retention factor, sometimes called our capacity factor, which we'll call little k sub a. We want to get that in between a range of like 1 to 5, and this is the formula for it. It's just the retention time minus the mobile phase time divided by the mobile phase time, or you could do it as TS over TM. Right? And so you want your retention factor or your capacity factor, which is calculated by TS over TM, to be somewhere between 1 and 5. Okay? We're going to see that there's going to be a relationship between big K and little k in just a second. Okay? We have what's called a selectivity factor, which is going to provide a measure of how well a column is going to separate different analytes. So in here, right, we've got, we're going to call this peak M, and then we got a peak, we'll call it A, and then let's say we've got another peak over here, right? We'll call this guy B, right? Where we've got a separation between A and B that is happening. We want to describe how good our column is at separating these different components. We're going to use what's called the selectivity factor. And that selectivity factor is just going to be the partition coefficient for B over A, or the capacity factor of B over A, or the retention time of B minus the mobile phase time for the whole separation divided by the retention time of A minus the mobile phase time for the whole thing. Okay? Where B is always going to be that second or more highly retained species. Could you call it A and B? Yes. Could you call it B and C? Yes. Whatever that most, so you could look between A and B, or you could look between B and C, right? And you get a different selectivity factor. And that selectivity factor is going to change based on what A and B are. And even on that same chromatogram, if I look at A versus C, right, that selectivity factor is going to be different than A versus B, or that's going to be different between B and C. So your selectivity factor really depends on what A and B are. Right? And A and B's physical and chemical identity determines how much you get partitions into the mobile phase and the stationary phase, which is going to show up as a difference in how long it takes B and A to elute from the column. So let's think back to that separatory funnel and that boundary layer. And that's where all the action was. So maybe you shook that sucker up, right? And then you got a bunch of little bubbles. Well, those little bubbles of organic phase, those little bubbles still have the surface area, and that was still, the surface was where that interface was, and that interface was where all of the exchange happened between the organic phase and the aqueous phase. So you can think of your column as being made up of a very large number of very, very small separatory funnels. So each time you do that separation, right, you're getting a more and more pure compound. We're also going to assume that all our curves are going to be Gaussian. Okay? And it's also going to assume that equilibrium is reached in the column. And it's going to be a dynamic equilibrium, right? Because remember, equilibria is not talking about the progress of an individual microscale molecule, but we're talking about all of them. And so we're kind of doing a little bit of fast and loose with kinetics, right? Because we're doing a big K, which is assuming equilibrium. And we assume equilibrium is no change in the bulk properties because at an infinite time, right? Whereas kinetics, right, you definitely have a kinetic time varying situation going on as you're flowing this thing through a column. And so our kinetics assume some sort of time base to things. And so we're kind of being a little bit fast and loose here. The actual details for that get really involved. So I'm just forewarning you and saying, hey, you know, this is a place where I'm deliberately being a little bit hand wavy and saying, okay, there's this equilibrium thing, and it's definitely not an equilibrium thing, but we're going to treat it as if it is an equilibrium process. So if you think about what's happening, right? We got some column, we've got it's got a particular length, right? We put our sample in, we got a detector out on the other side. If we look at our number of molecules, right, we can make a graph. At the end of the analyte profile at the end of the packing, right, we've got some sort of time that it's come out, and we have a distribution of molecules, right? And we're going to have some sort of H, which is going to be sigma squared over L. Sigma is going to be the spread of this data. L is going to be the length of the column. Right? So the length of the column is kind of determining where that mean is happening. It would also determine where that retention time is going to happen. And then we've got a spread, a Gaussian distribution, right? That's going to be the sigma, right? And we're going to assume that we've got +1 sigma and -1 sigma, and that you've got some sort of spread, right? So, you know, if you think about different, like, let's say age groups, going back to a race, right? So if you've got like 18-year-olds in one group, and then you've got like 80-year-olds in another group, right? You're going to come up with like the 80-year-olds are probably going to come in a little bit later than those 18-year-olds. But even within that group, some people are going to be faster and some people are going to be slower. So you're still going to get a distribution of times, just like you're going to get a distribution here as to which molecules are going to come out a little bit sooner and which molecules are going to come out a little bit later. When we are looking at these things, this is a very traditional way to do this. If you had to do it on paper, like you were stuck on a desert island and you do not have a computer, right? The number of theoretical plates in a column is very, very useful to know, but how do you figure that out? Well, you can figure out the number of theoretical plates by looking at how broad that column is, or how broad that peak is. If you've got a lot of theoretical plates, it gets really narrow. If you don't have very many theoretical plates, it gets broad. So the number of theoretical plates is going to change your peak shape, right? So when we talked about how do I make a separation more effective, and we said, well, we could move the retention times apart from each other, or we could sharpen them up. Making smaller theoretical plates, increasing the number of theoretical plates per column is going to be how you sharpen those peaks up. Okay? You can figure out how many theoretical plates are in your column by looking at the width. So you're going to take your retention time, and you're going to do 16 times the retention time divided by the width squared. Okay? And again, there is a lot of math that goes into doing that, but it's when you get it down to like this part, it's not hard, right? And you see this number 16 showing up, and you're like, oh, that's kind of power of 2-ish looking. Yeah, there's a reason why that's coming in for that. You are looking at W, the peak width, right? Not figuring out sigma, because if you were doing this by hand, figuring out and measuring the peak width is something you can do with a ruler, right? So, back in the 1930s, when they were developing all these techniques, you were plotting stuff out on a chart recorder. You were not throwing it into a computer, which would be like, all right, here's some digital data. I can come up with a sigma value and I'm good to go. So, you needed something that was measurable and easy to do. Right. So our plate height is going to be H. Our number of theoretical plates will be N. The length of the column packing, right, is going to be related to both of this. This is like one of those speed, distance, time things. So our number of theoretical plates is going to be the length of the column divided by the plate height. So how many plates do I have in? Well, how long is your column, right? And how thick are those plates? Efficiency decreases with an increase in N and with a decrease in H. So you want to make N big, you want to make H small, right? You want the very thin interface. You increase the resolution by increasing N for a given column by adding length. The cost is that you're also going to be increasing the time it takes for you to do that separation. So if you increase L, it's going to come at a cost of, well, now I've got this giant column, right, that's 3 feet long, and it's going to take longer for stuff to transit that column. So the plate height, there is what's called the Van Deemter equation. This is the historical Van Deemter equation. This is a nice analytical chemistry equation because it's like A plus B plus C. Right? It's not one of those, not a hard equation to remember, and I'll give that to you. But it's saying that in a separation, if I'm looking at computing my plate height is going to be related to 3 things. And remember, we want H to be as small as possible. There is an A term, which is related to eddy diffusion, a B term, which is related to longitudinal diffusion, and a C term, which is related to the mass transfer kinetics between the mobile phase and the stationary phase. So this term over here, that's dealing with our partition coefficient. The B term, right, is something that just has to do with the diffusion rate of the molecule, and A is about the path that that molecule is taking. So this guy is going to be path, right? Your path and your packing, right? This is like how many people are in the way of that beer keg, right? And U is going to be the linear velocity. So in other words, how fast are you pushing things through the column? So A is equal to the multiple paths taken by a chemical compound. In an open tubular column, that's going to be 0, right? So for example, right, in GC, right? So there is not going to be an A term in GC. There are no multiple paths, right? If you're in a packed column, you got different ways to go through, right? You got all those people to move around. If you have a space where nobody is in the way between you and that beer keg, that is a straight shot. You do not have the A term. B sub U is equal to the longitudinal diffusion of the particles in the compound. So this is that random path that those molecules are going to take. When you look at a molecule, it's going to diffuse in all different directions, right? A random molecule or molecule is going to take a random path to it, right? It's going to have a Brownian type motion to it, like a dust mote floating around in a sunbeam. And that's going to be divided by U. So the faster you can get things through your column, the better as far as a B term goes, because we don't have time to like wander around and get distracted, right? So the B term is the kitty cat term, right? You were trying to get to that beer, but it's like, ooh, cat, right? Or I'm gonna pet the puppy, right? So this is the faster you can push somebody through, the less distracted you're gonna be. The C term is gonna be the equilibration point. In a column, there's an interaction between the mobile and the stationary phase. This is where that C term comes in, and that's our partition coefficient. Right? If you plot all of these guys up together, you get this confusing thing, right? So you've got our B term is going to decrease the faster you go. So we're looking at linear velocity on X, and we're looking at plate height on Y. Remember, we want this number to be as small as possible. So the faster you push things through, the less you got to worry about B. Right? The faster you push things through, the more you have to worry about C. Right? So at some point, right, our decreasing and our increasing curves are going to have a minimum, and that's what this curve here, right, our composite curve, is all about. And so it makes this a very characteristic, almost check mark looking shape that's going to be where we're looking at trying to get something in the minimum, right? The minimum is what we're shooting for. And so that's saying that at some particular linear velocity, we're going to have an ideal for a given column flow rate. Right? So flow rate is one of those things that is important to us because it's going to set the number of theoretical plates, the number of theoretical, it's going to set the plate height. The plate height sets the number of theoretical plates. The number of theoretical plates determines whether you've got a broad or a narrow peak. So lateral diffusion, molecules are going to diffuse randomly. So this is our B term. Right? So our molecules are going to diffuse randomly, including with and against the flow. Right? So when we put all these molecules on top of our column, right, when we get all of our 80-year-olds in that race and we say go, right, some of them are going to run fast and in the right direction. And they're going to get a little boost and we're going to get a tailwind, right? Some of them are going to get confused and run the opposite direction for a little bit. Right? So when our molecules have that Brownian motion, they're going to move, right? The whole group is going to move over time, right? It's going to move from one spot to the next spot to the next spot. They're going to make progress over time. But because some of them were running the wrong way occasionally, they're going to run backwards. And so over time, your peaks are going to get broader and broader and broader. So this broadening that happens, part of it is because of this diffusion term. Right? And it's because the molecules are moving at random the whole time. So our column efficiency, right? This is our path one, right? So if you look at our A term, right? Not to be confused with the A team. All right, so if I've got two different paths, right? So I've got molecule 1 and molecule 2. This is our packed room. They're trying to get to be the beer keg at the end. One person has a pretty straight shot. The other one has a lot of interferences in the way. And so they've got two different path lengths that they're taking. This guy here is going to come out second, but it's going to increase the distribution. If you've got a column that is not very uniform, you have lots of multiple pathways that those things can take. So this is why you don't want to let your column dry out and get little gaps in it. You want to have your column packed with very uniform particles if you can make it, so that you don't have like a bunch of big particles on one side and small particles on the other side, right? So if you're trying to get to a beer keg and it's a room full of college students versus a room full of toddlers, there's probably going to be some differences in how fast you get there. Again, why there's toddlers are around the beer keg, yeah, I don't know. So that's going to lead to some broadening as well. In your Van Deemter curves are going to look a little bit different whether you've got a liquid or a gas phase chromatogram. Usually this gas phase chromatogram looks a little bit more flattened out, right? Because there's no effect from that A term, right? There's no differential path length broadening that's happening. So resolution is probably the most important thing that you can get out of a chromatogram. I mean, that's the whole point as to why you're doing it, is I'm trying to I'm trying to unmix these two things. Resolution is your peak separation. So let's define what that is. So if I've got two components, A and B, and if I look at where they are, right, if I looked at this and I had a yellow and a blue, I would have a bunch of green here in the middle where these two things interacted. Right? The better I am at pulling those two peaks apart from each other, the less green stuff I'm going to have. So is there some point when we can say, yes, I have separated my yellow and my blue, and I don't have any green, and these two compounds are resolved from each other. They are separated completely. And the answer is yes. Okay. At a value of R is equal to 1.5, the peaks are said to be completely resolved, and that's a 0.3% overlap. Right? So when you calculate this value for R, right, you are looking at, well, here is my peak position, my retention time. Here is the two widths for those things, and how much overlap do I have? And we're going to arbitrarily set a value of R is equal to 1.5 or a 0.3% overlap to say, yeah, they are sufficiently separated from each other so that we can say that the yellow and the blue part are not mixed anymore. We have completely unmixed them. Okay? We need a bunch of things to get a number for R. Right? So the things that are going to go into that are going to be our retention time and how wide these peaks are. Right? So those are the bases for, like, is it going to be resolved? Like, are the little feeties, are their little toesies touching each other? Right? Little feet and little toes on these guys. Or I'm going to draw a little foot, right? So we can draw a little foot, and he's got a little ankle, toe, give him an ankle there, right? And so are the little feetsies touching each other? That's supposed to be a foot. And so if they're touching, then they're not resolved. And so they're only just touching a little bit, 0.03%, then we're going to say they're fully resolved. So we need to know where the retention time is. So where's the peak of those peaks? Right? And we're going to need to know how wide they are. Right? So what's the distance and how, like maybe this dude over here, he's wearing a size 13, and maybe this person's over here wearing a size 9 shoe, right? So we can change the shoe size, or we can change how far apart they are from each other. The way we quantitate that using R, this equation here, it is not too bad. Right? Our resolution is coming from our retention time for B minus the retention time for A. So how far apart are they? And then we're going to multiply that by 2 for math reasons. And then we're just going to divide it by how wide those two things are at the bottom. Right? Now, could you throw this into some sort of computer and have the computer go through and do all the calculations for you? Of course you could. But this is a simple way to do it on paper if all you got is a ruler and you're looking at, well, how wide is this thing and how many seconds wide is it? Right? So keeping in mind that the units on here could be seconds, it could be minutes, it could be hours, right? So these are all going to be in time units. Right? So our retention time is not going to have any units because we've got seconds minus seconds, which gives us seconds over seconds plus seconds, which is seconds. Right? So this is the way to do it if you've got a chromatogram. So if you've got the thing in front of you and you can measure, both RT1 and retention time 2, and you can measure width 1, and you can measure width 2, right? Cool. There is another way to figure that out, and that is using N, right? Because N is going to tell you how sharp those peaks are, right? N is going to affect that width. So you can figure out for a given R how many theoretical plates you would need to get that separation given our selectivity factors and our capacity factors. Right? So if we rearrange that again, we can do a predict on what our retention time would be if we know what our resolution is, our theoretical plate height is, our selectivity factors, and our capacity factors are. Right? So we've got these 3 equations. They're all kind of related to each other. They're all related to R, and they're all describing where do my peaks happen and how broad they are. Right? And they're just solving and rearranged for different things. Now, finding T sub R based on all of these other things, there are some reasons why you would want to do that. I will talk about that maybe a little bit on Tuesday, but one of the things about retention times is or these capacity factors, right? You had to use retention time to kind of get those most of the time. But if you're looking at a resolution, you can actually predict what that time is going to be, and then there are some things where you can kind of do a prediction on what a compound's retention time might be. It's called the Kovacs retention index. If we got time, I'll talk about that. But for us, right, your be able to's are going to be, calculate R from a chromatogram, right? So, be able to do this, be able to do that, right? And be able to do this, right? Tuesday a review day or a class? It will probably be a class just because we only have, 5 minutes left, and we haven't really talked about GC. It might, if I can blow through the GC and the LC stuff on Tuesday and then open it up for review, I'll do that. Well, I will try to get it as I could assign you watching a video as homework and do review, if you guys would rather do that. Yeah, I will think about trying to do a list of topics. Let me put that on there. So the last couple of chapter homeworks, I will open them up. You will not be graded on them. You can have them to practice with. So list of topics. You know what? Maybe we can do that on Tuesday. So how about, as this week during the regular, yes, this is lab cleanup week. So you will get there at about 1:10. I will not keep you more than an hour, hopefully less. And then head on out for lab. So how about on Tuesday, we do a review, but that is coming at the cost of, I will make a video and you have to watch the video to get the rest of the GC and the LC stuff. Will the chapters you didn't cover still be on the final? No, no, I won't do that. That'd be mean. So basically, if there is a Zoom meeting for it, then yeah, we'll cover it, but not the stuff we didn't cover. We have plenty of stuff. What's an example of a short answer question? Draw and label the parts of an electrochemical cell. What define in your own words retention time? Let's see, sure, fill in the blank, right? So reduction happens at the blank, whereas oxidation happens at the blank. Will we be on camera for the final? Yes, you will be on camera for the final. I think I would get strongly yelled at if I did not insist on that. So when we do the final, everybody's going to have to open up the Zoom link. You're going to have to be on camera the whole time with your audio on, unless I tell you to turn it off because you're working in some horrible, noisy background place and disrupting other people. But yes, yeah, you will be on camera for the final. So we will make our list of topics that is important on Tuesday. We will go through and review stuff. Yeah, so I think that sounds like a good plan for Tuesday. But I will make the rest of this stuff, I will record that sometime over the weekend and post that. So you will be responsible for that next video that's coming up, and it hopefully won't be more than an hour, where we're just going to get what's the best review. I've gone through some of the practice exams to focus on the textbook or the homeworks. So if you've gone through the practice exams, that is probably your best thing to do, because it's going to give you an idea of the type and difficulty level at which the questions will be pitched. Next up, I would probably go through, if it was me trying to maximize my time, I would probably read the book to see if there were concepts I missed. Just trying to game the problem solving stuff so that I didn't have to go through all of the homework to review that level of detail. So like if I know how to do Nernst equation, right, I don't feel like I would need to go through and review 10 Nernst equation problems in the homework, but maybe there might be something I would have missed conceptually in the book. So, but that's just me, right? I don't know what you don't know, so it's hard to say, yeah, do this or don't do that. Homework is always good because it gives you specific examples, right? And so that's very useful practice to have. But I think at this point, if it were me, I would focus on more broader concepts to make sure I've got those down. And then if I feel like I'm deficient or I'm missing something, then I would go through and like, okay, well, I need to figure this out, right? So, if I were to give you a chromatogram, could you, calculate an R value for me and say, is it resolved or not resolved? And yeah, sure, do that. Maybe do one of those. But the study guides correlate to the chapters in our textbook. That's from a previous class, right? So those are like general, broad. They're old. They are not necessarily going to be relevant, but they are going to break down some of those key concepts. And like, yeah, these are things that are important to know from each of those chapters. Yeah, so those are not a bad resource. Just be aware that they're not necessarily going to be, yes, this chapter corresponds to this chapter, and this is necessarily something I'm going to be covered, or something that is going to be necessarily show up. So, there might be stuff in there that we didn't cover, and there might be stuff that we covered that isn't in there. But it's a really good starting place because it's kind of nice. It's got a little outline. It's like, okay, these are some important things. Right. So the really hard questions are at the end of the sampling assignment. Should we expect questions like that on the final, or the simpler questions? Probably the simpler questions, because you've only got a finite amount of time, right? You've got a finite amount of time, and I got to cover, statistics, acid-base titrations, electrochemistry, electroanalysis, separation, spectroscopy. There's so many things to cover, right? If I asked you a complicated multi-part question, it's going to be really hard to make it a reasonable exam that somebody could get done in a sane amount of time. All right. Cool. Other stuff about the final. Okay, not seeing anything. If you guys do have other questions and you think of them, just let me know. Feel free to email me. The final is an opportunity. View it as, will you label the equations? No, I'm not going to label them. You're just going to get an equation, and it's going to be like, you got to figure out what it is. So you're not going to see something that's like, here is your formula for resolution. It's going to just say RS is equal to 2TRB minus 1TRA. And it's up to you to know which equation to do when. You can print it off before the exam. Yes, sure. So things that you're going to be allowed to have, you can have that equation sheet. You will have your note card front and back, right? You can have some, as much paper as you want, but it's got to be blank paper. Right? So you can use as much scratch paper because you're going to be writing stuff out longhand and scanning that in. All right. Cool. Anything else? Negative. All right. There is, and I have to reload. So one of the downsides about this whole, like, we're going to do everything on Zoom is that Canvas has a finite amount of space for each course. And what I have been doing is uploading all the videos from Zoom into into our Canvas course. So the problem is that it ate up all the space that was allocated for that course. And so I needed to delete 2 videos, and I will repost them to the YouTube channel so that you can watch them on the YouTube. Hopefully it will be a pretty seamless link for that, but right now there are 2 missing videos. So do not freak out if you're like, oh my gosh, electrochemistry 2, I think, and then there was another one, got deleted and they're not there. I have them, I just need to figure out where they are on my computer, upload them to YouTube, and put the corresponding link in there. But yeah, if you got questions about that, then, again, email me. All right, cool. I am going to stop this, and then I will upload our stuff on separations, keeping in mind that there will be a second one coming that I'm going to make you guys responsible for watching over the weekend, okay? So that we can do all of our review on Tuesday. Cool? All right. See you guys later. Peace out. Have a great weekend.